Hello again. So let's continue. This is part 2 of the talk, and let's just recall where we stopped in part 1. So we talked about the examples. Here, we explain where these indices come from for these trivial examples, and we mentioned Fisher-Kobe result that connects the Morse index of the self-shrinker to the number of negative eigenvalues of a differential operator in a weighted L2 space. Okay, and the operator is the Jacobi operator. The Jacobi operator for the Gaussian. Okay, let's move on to the motivation, or rather the motivation for the main result, right? We already talked about motivation to study self-shrinkers. Now let's go motivation where the result comes from. And again, just written down here the reminder that self-shrinker is a minimal surface in R3, but with a different metric, and that metric has positive Ricci curvature. That's why we expect the behavior to be similar. So let's first mention some results on minimal surface, some index estimates for minimal surface. So first, I want to mention Ross result, 2006. You have a minimal surface of genus G in R3, and the index is greater or equal than 2/3 of the genus. Okay, 2G divided by 3. And the idea here is to use harmonic one forms. We have 2G harmonic one forms on a genus G surface. And that corresponds to, by duality, corresponds to a vector field using the metric. And then you use the coordinates of that vector field in R3. So we have x1, x2, x3. Use the coordinates of that vector field as test functions for the second variation formula. Okay. I'm not going into details yet, but this is about minimal surface in R3. R3 is a flat ambient space, and we want to understand minimal surfaces in a positively curved ambient space, right? Because that's the analogy of self-shrinkers that we have. There's this result by Savo in 2010. If you have a minimal surface of S3 in genus G greater or equal than 1, so not the equator, then the index greater or equal than G over 2 plus 4. Okay. Of course, if genus is 0, it doesn't work because the index of the equator is 1. Let me just mention, Savo proved a lot more than this result, but that's what's summarizing what's relevant for what I want to say here. Okay, and now, unfortunately, Ross's method doesn't work because of the curvature term. Okay, and this comes up in the calculation when you if you use Ross's method as test functions, then there's still this curvature term in the calculation. It's not. It doesn't help you, right? So Savo came up with a different idea. So for a pair of vectors, for constant vectors in R4, so S3, right? I mean, sigma 2 is in S3 and S3 is in R4. Then he defines this. I'm going to define this later. This XUV corresponds to the infinitesimal generation. Infinitesimal generator of rotation along the plane defined by UV. Okay. And then he uses the so if alpha is a harmonic one form, or rather the the dual vector, right, using the metric, then he uses the average of these functions as test function. Okay, average over all UV with norm 1. I'm being a bit vague, but the idea is, the point is that Savo gets this test function that when you plug it in the second variation formula, it eliminates the curvature terms. Okay, as long as the curvature is positive, as long as the Ricci curvature is positive. Right? When you take the average of everything, I'm gonna go into more details a little bit later, because this is very relevant to us, because this approach that helps us deal with the curvature that comes from the incomplete metric, right? And now finally, more recent result by Shodosh Massimo. You have a minimal surface in R3, genus G, and number of ends K. Of course, all minimal surfaces in R3 are non-compact. Then the index is greater or equal than this number 2, number of ends R, right? G plus R minus 1. 2/3 of G plus R minus 1. Okay. So here, this index estimate improves Ross's index estimate and includes the ends. So the presence of ends contributes to index. Too many ends, right? So the idea, right, there are no more than 2G harmonic one forms in L2. So they look at a bigger space. So they look at weighted space for some weighted measure I'm not going to talk about. And then with this, in this weighted measure, there are extra harmonic one forms, but the index remains the same, right? It's so Fisher-Colbr's theorem for a certain weighted measure that they choose appropriately. The index of, so the number of negative eigenvalues remain the same. So you have more test functions, but the index is the same, right? So they use these extra harmonic one forms to produce more test functions that end up being negative directions. Okay. Sorry, the coordinates of the harmonic one forms, the test functions. Okay. So this is relevant for us because it shows us how to detect the ends of your critical point, right, of your minimal surface. So the main result here is just a combination of these 3 results, right, or rather they're the last 2 results, but inspired by Ross's method. That's sort of an original method, and changing appropriately to the self-shrinking setting, right? So this is the main motivation, these 3 results. Let me just mention that there are other index estimates for minimal surfaces that don't involve the genus. For minimal surface, there are upper bounds for the index in certain cases, and the index estimates for minimal surfaces is a much larger theory than what I'm summarizing here. This is just what's relevant for this talk, for this result. All right, and let's finally write down the main result. And here it is. You have a properly immersed orientable self-shrinking surface genus G, R asymptotically conical ends. Right? So I'm not looking for cylindrical ends, just looking at the conical ends. And the index is greater or equal than 2G plus R minus 1 divided by 3 plus 1. So this formula is fairly similar to a less refined, right? Similar to this one, a less refined. And this is the lower bound for the index. Okay, so Well, like I said, it's just a combination of previous results for minimal surfaces with the appropriate adaptation. So instead of harmonic forms, we use Gaussian harmonic forms, right? Harmonic forms are critical points of the L2 norm, and Gaussian harmonic forms are critical points of the L2 norm with the Gaussian weight. And this is equivalent to saying that d omega is equal to 0, so it's a closed one form, and co-closed one form, but this is a weighted co-close operator. So it's the dual to the differential operator with respect to the L2 weighted norm, this one. Okay. But there's just two differential equations, right? Okay, so Gaussian harmonic forms come naturally in that sense. It's completely analogous to harmonic one forms, right? You put in your weight in the function, the area functional, and then you put a weight in the L2 norm. Harmonic forms are just critical point of the L2 norm. Okay. So if you look at the second variation again, right? This piece of the second variation here of the Jacobi operator is just the weighted Laplacian, right? So this is equivalent to saying that the weighted Laplacian is equal to 0. That's why this Gaussian harmonic forms are relevant for the same reason that harmonic one forms work well in the calculations for minimal surfaces, right? Okay. So these are Gaussian harmonic one forms. Now, how many Gaussian harmonic one forms? Unexpectedly, it's similar to harmonic one forms. Okay. So we're looking for L2 mu integrable harmonic Gaussian harmonic one forms. So let's define this H1 mu sigma, the space of Gaussian harmonic forms omega with finite L2 norm. Okay. So if sigma is self-shrinker with genus G and R asymptotically conical ends, then the dimension is at least 2G plus R minus 1. Now let's see why that happens. So first, let's see where the 2G comes from. So the idea for each genus G, so let's look at this picture. For each genus G, I think I don't need to draw anymore. For each genus G, you have this G disjoint closed curves. So near these closed curves, you can find a closed one form, but it's not exact, right? So it has compact support near these closed curves. Okay, so each one form is the support is disjoint. They're linearly independent, and they're not exact. So the idea here is to solve the Gaussian harmonic form equation, the two equations above. So they're already closed. So I need to solve the co-closed equation in its cohomology class, right? Is closed but not exact form. And then, okay, you solve it, and it turns out that they are linearly independent. Okay, so this, you get G solutions, so G Gaussian harmonic forms. And if you put the Hodge star here, then you get 2G solutions. So here again, we're using dimension 2, right? And okay. And by construction, well, because it has compact support, then it has finite L2 norm. So this is the easy part of the construction, right? So now to construct the ends, right, to detect the ends, we need to construct a different kind of Gaussian harmonic one forms. Okay, this one is pretty straightforward. This is just the looking at these non-trivial curves. And the 2G comes from just using the Hodge star operator. Of course, if these ones are Gaussian harmonic, when you if you put the weighted Hodge star operator, then they're also Gaussian harmonic. So it's with respect to the L2 weighted product. Now for the ends, so the idea you fix one end, fix one of the ends, and then you take this, say for example, these two curves. Say you have three ends, right? You take this one curve coming to this end, and another curve going to the other end, but they coincide. They coincide here. Okay, they split at some point. They coincide here. So you have these curves. This one forms in the same way that you construct for the other one. You have this one forms. They're closed. The support is near each curve. So since they go to different ends, they have this joint support in certain part, right? So they're linearly independent because of that, and it's closed and not exact by construction. And here is where we use the ends are conical. So the idea is that we construct these curves at infinity near the ends using conical coordinates, like in this picture here. So in the cone, they have finite L2 mu norm, right? So this is a direct calculation. Since the ends are very similar to the cone, then it should have L2 mu norm in sigma as well, right? Because if you take a sufficient large compact set, then the metric is more or less the same. So it's comparable. So the L2 mu norm is also comparable. So this is, again, it's nothing unexpected, right? And as before, we can solve the Gaussian. So that's why they have finite L2 norm. That's where we use the ends are conical. And as before, they have you have a certain number of linearly independent Gaussian harmonic forms. Okay. You can't use the star operator because it's not clear if they're still linearly independent. Okay, when you start. For these ones, you can prove that there's this 2G are linearly independent, but if you start here, it's not clear that they're linearly independent. So you get a 2G plus R minus 1 number of Gaussian harmonic one forms, linearly independent Gaussian harmonic one form. So the dimension is at least 2G plus R minus 1. Okay. This is how you get the Gaussian harmonic one forms. This step is just PD. Okay. The geometry is all contained in this picture. All right. So this is how you get a certain number of Gaussian harmonic forms. So how does this connect to the index? And this is the key step by Impera Remoldi Salvo. And this is, this is the core of the result. So they prove that if you have a complete self-shrinker in R3, and index is greater or equal than 1/3 of the dimension of that space, right? So it connects everything, right? And let me just give a very, very sketchy idea of how to prove this. Very, very sketchy. So suppose And this is roughly how you prove the minimal surface case as well. Suppose the index is I and k is a dimension. Suppose by contradiction that I'm assuming that the index is finite. If the index is infinite, the inequality is trivial. Suppose the index is finite. And suppose the inequality is false. Suppose by contradiction. So this is by contradiction. So you see this. This is the contradiction of this, or of the original inequality. Then you define this test functions, right? So for each Gaussian you fix pair of vector fields in R3 and a Gaussian harmonic form. This is actually the dual vector, right? So this is a one form and this is a vector field, right? Psi is a one form and this is a vector field. So you define this function here in sigma, okay? And these are going to be our test functions, right? So this is Szavo's test function. Similarly defined to how Szavo did it for minimal surface, for minimal surface in S3. And Fisher-Colbury says that there are eigenfunctions corresponding to negative eigenvalues, right? Here. And then the next one is positive. Okay. So the idea is, because of the contradiction hypothesis, it's simply the fact that we can solve a system of equations, right? So there exists it's just a computing dimensions, right? This is this linear algebra, okay? This is a linear algebra for all I and for all V, W as well. So for all V and W in R3, so these are constant vectors, you can find at least one psi. So it comes from the fact that these dimensions are this dimension is very large. K is larger than this number, such that this is equal to 0 for all eigenfunctions. So by the min-max characterization, given Fisher-Colbury's result, the second variation has to be positive because it's perpendicular, it's L2 perpendicular to all of the negative eigenfunctions. That the eigenfunctions correspond to negative eigenvalues. Okay, and that is for all V and W, right? So what they do, they take the average of all of this for all V and W. So you fix, instead of R3, you look at all V and Ws with norm 1, so in S2. And they put a certain measure in S2 cross S2. It's not relevant, it's just a measure. And it turns out when you do this calculation, this number here is negative. Okay. And that's a contradiction. All right, so this is a direct calculation. All right. And taking the average is where the positive Ricci part comes into play. That's how you deal with the Ricci curvature. I know this is very sketchy, but it's a brief summary of the result. And now I just want to say that they proved a lot more than this. They prove index estimates for F minimal surface. So instead of the Gaussian area, they put different weights as well, and it also works. So for for some weighted measures, they prove the similar index estimates or even better index estimates. And they also prove it for higher dimensions. Okay. for us, the dimension 2 becomes relevant to construct to construct the Gaussian harmonic one forms that detect the ends. Okay. So that concludes the proof. Imper remotis salvos result together with this Gaussian harmonic one forms proves the desired inequality. So just a quick summary of tools that we used here. First, the Fisher-Colbert type theorem. So relates the index of the quadratic form on functions with the index of an operator in L2. A suitable test function has potential negative directions, and here is where the geometry comes into play, right? How to define a suitable test function, how to find a suitable test function. And the third step is, if you have too many test functions, some of those test functions must be linearly independent, and then quantifying what is too many, what is some, comes from these calculations, right? So the geometry comes in step 2, and the method comes in step 3. Right? And this sort of ideas can be used in other geometric problems as well. And it has been used for other geometric problems as well. But this is sort of like the rough thought process. All right. And like I said, I promised some questions. So first, suppose sigma has some sort of like symmetries. Can you prove a similar bound for equivariant index? Right, for different constant here, maybe, I know. So equivariant index is when you compute the index only with respect to equivariant functions, right? If you have some symmetry. Again, I mentioned this as well. It's expected that the cylinder is the only subshrinker with cylindrical ends. So, but if you ignore the expectation, can you prove the same bound with conical ends? I imagine that it also works. It shouldn't be too difficult to work with cylindrical ends instead of conical ends. And third question, and it's straightforward, right? Are there any index upper bounds? I'm not sure. There should be for surfaces, and I think maybe in certain cases that it has there are some results about index upper bounds in some special case. I'm not 100% sure about that. Okay. So I'm going to end here. Thanks for listening to my talk, and have a nice day.